Just to jog your memories, we said this. We said work has a specific meaning. You do work on an object. Brian, we said that work was equal to force times distance. It was a scalar, no direction. The units were Newton meters, force times distance, but it was such an important concept, we decided to give it a name. We called it a joule. This is the easiest equation for work. Colton, it's also the least useful because it's the most restrictive. It only works if the force and the distance are in the same direction, and it only works when the force is constant. Then I looked at one specific situation. I said, for example, one, I like example one, I like example one. We found the work done in lifting, and we said, you know what, you could calculate by going MGH, because you're lifting against gravity. We said it's actually force lift times the height. I don't know force lift. Oh, but look, it's the same as mg, so we said it's mgh. We said one of the nice things about work, because it's a scalar, this concept of force times distance, we use this all over the place. If you know you have to do a certain amount of physics work, but you're unable to apply the correct force, if you can come up with a clever way to increase the distance, you can lower the force. I think I alluded to the 5, or is it 6, I can't remember now, simple machines. But basically, much of our industrialization is coming up with clever ways to trade off bigger distance for smaller force. We're going to watch a video about that a bit later. And we got to here. But we want to be block D, Mr. Dewick. And it says record lesson to make sure I don't forget. Force times distance only works if the force is constant, is unchanging. What if the force is changing? You're going to end up with 3 definitions of work, and it's a mental checklist that I go through. If they ask, how much work? First thing I try is force times distance, which, no pun intended, will work a lot in Physics 11, not in Physics 12, when we get to more interesting questions. The second definition is this next one. Work is also the area under a force versus distance graph. I didn't put this on your formula sheet. Well, I sort of did. I'll show you how I hinted at it in a little bit. It's the area under a force versus distance graph. Matt, can you read to me example 7, please? Stop. How much what? Now, normally I might try going force times distance, but I noticed they gave me a graph. What's on the y-axis, Matt, my friend? What's on the x-axis? You know what? The work is going to be the area. And also, Matt, I notice the force was constant for a bit, but then all of a sudden it started getting bigger and bigger and bigger and bigger. I can't use force times distance. It wants me to find the work moving the object, Matt, from where to where? Okay. Everybody, if you would be so kind, draw a little dotted line from the 2 going straight down and draw a little dotted line down to the 5. Draw that in. But then don't write this next bit down. Keep watching and I'll tell you when to write. What we want to find, Matt, is this area. Don't write this down. We want to find the area of that. That shape has a name. It has 2 sides that are parallel and 2 that aren't. Does anybody know, what do we call 2 parallel sides and 2 that aren't? What do we call that shape? You're right. Trapezoid. It's a trapezoid. Okay? I always ask, does anybody here know the formula for the area of a trapezoid? Because there is one. And often my international students know it because Europe teaches it. Certainly my students from Italy, they always know it. The reason we don't teach it in North America, Colton, look up, is because it's redundant. Any trapezoid can be broken into a triangle and a rectangle. Redundant means you don't need it. It's unnecessary because you've already got it. You have the area of a rectangle. You've been taught that somewhere along the way. And you will need to know that area formula. And you have the area of a triangle. You've been taught that, and you will need to know that. Although I'll live with it if you add both of those equations to your green sheet. But only do that at the end of this unit if you think you need to. It's nice if you have them up here. So I said don't write this down. Here's what I would like you to write. Can all of you draw a little dotted line across like that? And Sesame Street is brought to you today not by a trapezoid, but by a triangle and a rectangle. I'm going to call this area 1. I'll just put a 1 with a circle on it. Lazy but organized. What do I call the bottom area? 4. Oh, 2. That's much smarter. That works. Yeah, 2. And I'm going to find the area underneath shape 1, and I'll write it. My abbrev for area is capital letter A. Why don't I use a lowercase a for area? What does that mean in physics? Yeah, it's already taken. It's a triangle. Anybody know the formula for the area of a triangle? Gerard. It's a half base times the height. I'm lazy, so I write it as base times height over 2. I don't bother writing the 1 part of the half. One of the most common silly mistakes kids make is they count squares instead of looking at the scale. Make sure you look at the scale on your graph. Brian, you're with me? You're not foolish looking at your phone or anything? Make sure you're looking at the scale on your graph. Let me give you an example. So here's the base. What number is right here, Gerard? What number is right here? What's the base length? What number is right here, Gerard? What number is right here? What's the base length? 3. 5, take away 2. Don't count hash marks, subtract. Okay? So what's the base length as a number exactly? Good. What's the height? Some kids might go, 1, 2, 3. Is each hash mark worth 1 on the y-axis? Look at the scale. Matt, what's the highest this triangle gets? Where does it start? Not 1, but 2. So, 8 high, start at 2. What's the height? Not if we start at 2.
6.
Thank you. Higher, take away lower. Right? That's really what you're doing. Either in your head or use a calculator. I don't care. So it's 3 times 6 divided by 2. 9? Yeah? Yeah? 9? And that would be joules. Then I would find area 2. What's the area of a rectangle? Length times width. Again, what's the length of this rectangle? Starts at 2, ends at 5, 3. What's the height of this rectangle? Not 1. Look at the scale. Each hash mark has to be worth what, Matt? If that's 4, what's each hash mark worth? Not 1, but yes. So 2 high, 1 a hash mark, but you got to look at the scale. Drives me crazy when I see it's 3 times 1. No, look at the numbers, please. In your head, Matt? And you might even be able to add 9 plus 16 in your head, can you? How many joules of work did we do in moving this object from 2 meters to 5 meters exactly as a number? 15. How do I know when to use this method? It'll be fairly obvious. They'll give me a graph of force versus distance or displacement graph. Yes? So what was that? Which 3? The top one or the bottom one? They're different. So this 3 is I went 5, 2, 3. Yeah, you're right. It's the same for both of them. So look at the scale. If you're doing a base, it'll be furthest minus shallowest. If you're doing a height, it'll be highest minus lowest. Or whatever words you want to use. Is that all right? Okay. So now we have 2 definitions of work. The first one, work is force times distance. This requires a constant, unchanging force. We also have the area under a force versus distance graph. I abbreviated force and distance, if you don't mind, because I can.
It says displacement.
Distance and displacement will both be okay because it's a scalar. I was wondering who would catch that. This class, someone will speak up. Nobody called it on the last one. You can all turn the page, but just for nerd trivia, I don't know, it may have been this class. Where this really comes in handy is next year we start looking at rocket science. As you go further and further from Earth, what happens to the force of gravity? If you graph that, the force of gravity times your distance from the Earth, it actually looks like this. And so you end up needing some calculus to find the area under a curve. But that there, because work is how much energy, tells you how to calculate how much rocket fuel you need. It would be that area. You would need to know how many joules per liter of whatever rocket fuel you can get, but that would tell you how many liters of rocket fuel. In case you're wondering. But that's next year. Example 8. Tyler, what did they ask me to find in example 8? Work. Did they give me a graph? I'll bet you it's going to be the area. We're moving from where to where? Moving this object. How far? The question tells me. Yeah, and I guess we'll assume we start at 0. In other words, all of you can draw a little dotted line at 0 like that, a little dotted line at 10. Don't write this next bit down. It's going to be that area, except what shape is that? It's a trapezoid. So on your test, on your quiz, if I give you an area, it's going to be one of 3 shapes. It's going to be a rectangle, length times width. It's going to be a triangle, base times height divided by 2. Or it's going to be a trapezoid, which is both of them put together. I can break this into a triangle and a rectangle by doing that. Add that dotted line in. Lazy but organized. I usually call one of the areas area 1 and the other one area 2. So I'll call this area 1, this area 2, area 1. Tyler, what shape is area 1? Area 1?
Oh.
Thank you. What's the area of a triangle? It's base times height divided by 2. If you don't know that, you might want to write that somewhere on the front or back of your formula sheet. And again, how long is the base? A common mistake, some kid might say, 2 because it's 2 squares. Look at the scale. We start at 0, we end at 10. How long is the base? 10. What's the height? A sloppy mistake, Tyler, a kid might say, 30! No. Where does it start at? 20, ends at 30, so divided by 2, because it's a triangle. You might be able to do that in your head. 10 times 10 divided by 2? 50. And that's joules. The second area, I'll change colors, is going to be area 2. It's a rectangle. What's the area of a rectangle? Length times width. Tyler, how long is the base of that rectangle? 10 again. What's the height of the rectangle? Good. You might be able to do that in your head. 20 times 10?
Just add a 0. Just add a 0.
200, right? And I'll bet you can add 250 together. In fact, I think I accidentally just said the answer, didn't I? 250. Now, you might be saying, Duke, what's the point? There are other things that work relates to which actually make this very useful, such as the gravity analogy I gave you earlier, the illustration I gave you earlier. Okay? Example 9, let's put it all together. This is a much more challenging question. I'll probably give you one in your homework. I'll probably give you one on a quiz. Don't know if I'll give you one like this on the test. So I'm not necessarily saying I like this question, I like this question. I might change my mind. If I do, I'll let you know. Okay. A box is being pushed along the floor that has a coefficient of friction of 0.25. You know what? As soon as I see this, I'll bet you there might be a free body diagram in my future. Okay? The person pushing applies a force of 525 newtons over a distance of 22 meters. Ella, what does A want me to find?
Work.
Keep reading.
How much work is being done by the person pushing?
The reason I said keep reading is what does B want me to find? Work. Okay, we're going to have to be a little more careful now. I would definitely start out by writing down, is there a graph? Be obvious. I would say, well, maybe work is force times distance. You know what? I think it's going to be the pushing force if it's the work done by the person pushing. And if I have more than one force in the question, I will be very clear which work I'm asking you to find. I'll use the word. Well, Ella, what is the pushing force in newtons exactly? Sorry? Yep. Distance? And I'm imagining this, I think they are in the same direction, so we're good. Can you give it to me? Give me all the sig figs, all the digits, please. It's going to be a little more than 10,000, probably in the 11,000s.
11,550.
11,550 units, work?
Joules.
Yeah. That's the total work this person did. That's how much food energy this person burned and in pushing this object. But not all of it went into the box. If there was no friction, all of that energy would have gone into making the box speed up. But there is friction. Noor, what's B you want me to find?
How much work is that over?
I'm going to argue that that's probably the force of friction times distance. And I'll even put an FFR on the work done by friction or overcoming friction, force of friction times distance. Do you know the force of friction? No. This is a job for a free body diagram. I'm going to do a really quick one over here. And I left some space there. What are the forces acting on this box, Colton? Get the obvious one. Yep. Are we sinking to the ground like quicksand? Or are we flying? Okay, normal force. Same size as mg. Noor, what else? We called that F applied. But you know what? I called it F push. I wouldn't care if you wanted to say F push to be consistent with your notation. Go ahead. So, sure, let's go F push. It's 500 and whatever. What else? Which way? And I'm thinking it's smaller. Okay. I've got the visualization now. I can see how all this is related. Let's keep going. Friction. What can I do with FFR? What can I do with friction? Oh, mu times the normal force, you say. You get that right from the green sheet? Okay. Oh, I don't know the normal force. Oh, but look. I don't know the force the same size as the normal force. Okay. I think I can write this as the work done by friction is mu mg times d. It's going to be 0.25 times 124, g 9.8, 22. And can you give me all the sig figs when you're done, please? Noor, my angel. Six, 6,683.6. Okay. For a candy, can anybody tell me the very subtle problem here with this answer? Who remembers what restrictions I gave you for the work equation? What I said had to, there was two things I said had to be the case. Has to be in the same direction. Which way are we moving in my picture to the right? Which way is friction pointing? Okay. Here's what this means. I should have said the force and the distance need to be aligned with each other in the same line. Fancy word, in the same plane. They're in opposite directions. What that means is we're losing energy to friction. What would be a good way to show that we're losing energy to friction? Because the force and the distance are in the opposite direction. By the way, I've given you a lousy explanation. Sienna, it's because it's really force times distance cos theta, and in this case, theta is 180 degrees, and the cosine of 180 degrees, as everyone knows, is negative. A lot of what I'm teaching you this year, if you take Physics 12, I can give you a more nitpicky, fussier, but better, this is why explanation once we start looking at vectors and components and things. Okay? All right. All right. Jesse, what does C want me to find? Draw a little line like that. Well, Jesse, if the work done in pushing was force push times distance, and if the work done by friction was force friction times distance, what do you think the net work is going to be? Spot the pattern. More specific. Which F? No, that's up here. Work done in pushing was the force pushing times distance. The work done by friction was the force friction by distance. The work net is the force. Help me out, folks. Net times distance. You know what the net force is? Winner minus loser. Really quickly, how big is the pushing force? 5 what? 525, that's the pushing force. Minus, how big is friction? Mu times the normal force. Do you know what the net force is? It's that. Did I do that correctly? Mu times the normal force. If I go that times, what was the distance? 22? I made a typo somewhere. Where's my typo?
0.24.
0.25, Mr. Dewick. Thank you. Let's go like this. Okay, 0.25 is what happens when I go from memory. That's the net force, 221.2. And if I multiply that by the distance of 22, that's the net work, 4,866.4. And that'll get you there. And I'm fine if you do it that way. So why does that work? No pun intended. By the way, unfortunately, the word work in English has a different meaning. So why does that work? I don't mean why does that force times distance. I mean, why does that function? Why is that acceptable? Well, if work pushing is force pushing times distance, and if the work done by friction is the force of friction times distance, I'm telling you, the net work is the net force times distance. There's another way that I would probably do this. You know what I would say instead? And this is why we drew a line. Work equals, so here's the net work. What's the total work we did in part A, Gibson? What's the total work we did in part A? That's how much work this person did minus, Noor, how much energy did we lose to friction? It's the one that you did.
6,680.
All the digits, please.
0.6.
It would be really cool if you go on your calculator, if you go that minus that. It would be neat if you get that. Do you? What we're saying is this. If you happen, Jesse, from your free body diagram to know the net force by just going winner minus loser equals F net, you can go that force times distance. Or if you happen to know how much energy you put in and how much energy you lost, well, if you subtract those, that's the net work left over. That's what's left over. That's the net work. So you get the same answer both ways. What's your homework? Every question, but you can skip number 4. I love it. Every one of you looked and was all so eager. Oh, I'm going to cross that. Do it! That's not nice. So let's talk about this. For number 1, straight plug and chug. How much work? It's going to be force times distance. Number 2, now you're climbing stairs, you're lifting. It's going to be something, are the one that we generated for climbing stairs or lifting. Okay? 3 is good. 5 is good. 6 is good. 7 is good. 8 is good. Number 9 is very similar to number 9 that we just did, example 9 that we just did. So my hint is, before you ask me a question, look at example 9, Noor. You with me? Not looking at your phone or anything foolish? Okay. Number 10 is the area question on the next page. So if you look, part A wants the work done moving from point 4 to point 6. Don't write this down, look up. That's going to be that area. Then part B wants the work done moving from 0 all the way to point 8. That's going to be this area, which is just a triangle, base times height divided by 2. And then there's a part C. The answers are at the very, very bottom here. Okay? But first, put your pencils down and look up.